Thank you very much, and thank you to all the organisers. It's a great pleasure to be here tonight and on the same platform as Henrik. Now, in this talk, I'm actually going to start off talking a little bit about science, and in particular, science in the modern world, because I do think that a lot of the misconceptions about climate science are actually misconceptions about science in general. So bear with me to start with. So what is science? Okay. If you look at dictionary definitions of science from 100 years ago, they all concentrate on the fact it comes from Latin for knowledge, and it is knowledge, but it's a knowledge of a certain type that's arrived at in a certain way. And then over the last century, increasingly, the words science community and science consensus crept into the definitions, particularly led by this man, who was a condensed matter physicist from New Zealand. So what is science consensus? I searched around for a dictionary definition, and I found this on Wikipedia of all places, and I think it's excellent, okay? The collective judgment, position, and opinion of a community of scientists in that particular field. That matters. Scientists often don't realise that their expertise and skills are very well honed to their discipline, and they think they can apply it somewhere else, and it's quite often not a good idea. So that in that field of study is an important caveat. It implies general agreement, though not necessarily unanimity. Now, this is my community. It's actually one of two communities I belong to, because I'm a solar terrestrial physics, and this is the world's solar physicists that we got together for a meeting in Bournemouth a couple of years ago. And there are some things about the sun that everybody in this picture would agree on. Everybody. There's some things that 95% would agree on. We'd say there's a consensus, but not unanimity. And there are some things we don't agree on. And of course, if we had unanimity, we wouldn't need to meet to discuss, would we? There'd be nothing to discuss. And so there is always that element to science that there's an edge where there isn't consensus. Why it's important is a lot of people have an image of science that's based around, particularly this man, a sort of lone wolf who turns everything upside down. It was actually never thus, okay? Einstein, there were a whole load of people pushing at the doors he opened, okay? And as actually even Newton managed to say, he saw further than most by standing on the shoulders of giants. And that was true of Einstein. So that model is wrong, and the modern model for science is very much the consensus model, okay? There are reasons for that. If you look at Einstein's miracle year in 1905, the number of scientific publications was smaller than that in the year 2000 by a factor of about 1 million. Okay? Science has become much more discipline-oriented, it's become interdisciplinary, multidisciplinary, and there's just much more of it. And that's why one individual doesn't matter as much as the consensus. So how do we arrive at this famous consensus? And it's through a process that I think, and many others do, is Britain's greatest ever contribution to science, and that's peer review. Okay. It was actually introduced, ironically, by an immigrant to this country, Henrik. He was the first secretary of the Royal Society and the first editor of the world's oldest scientific journal, Phil Trans. And he started pushing things out where there wasn't consensus to his friends and fellows of the Royal Society to see who thought what should be published. And his ideas were then taken up by Sir Roger Bacon and John Deere and formalised into what we understand today as peer review, what we would recognise today, first applied to medical observations by the Royal Society of Edinburgh. Why is it so important? Well, to put it in modern parlance, it's the way science expunges fake news. Okay? It's incredibly frustrating, peer review. It's often flawed, it's slow, it drives you mad as a scientist, but it will get rid of what's wrong in the literature record over time for a certainty. Sometimes it does it very quickly, like cold fusion. Sometimes it takes a long time. And if you want to know what would have happened without peer review, I'll give you the internet, okay? It's not an information highway anymore, it's a misinformation highway. There's more wrong on the internet than there is right, as observed by Randall Munro here. Okay, so that's why peer review is important, that's why consensus is important. Well, let me actually give you an example. Let's go back to Einstein again for a moment. Einstein's relativity, introduced in 1905, and then general relativity 10 years later. And it kind of divided the scientific opinions. There was people greatly for, people greatly against. And in 1919, Sir Arthur Eddington here discovered what we now call gravitational lensing, a prediction of Einstein's theory that wasn't in Newton's. And the consensus started to shift very, very rapidly behind Einstein. An element that people don't realize is Einstein was a liberal pacifist Jew, and I'm afraid in the 1920s that was not popular around the world, but especially in his native Germany. There were public outcry about it. Believe it or not, Einstein's relativity was described as Jewish physics. It was all a Jewish plot to befuddle us, to make it easier for other Jews to take our money, our women, and our jobs. Seriously, this actually happened. There were huge events. Einstein became so fearful for his life, he stopped talking in public. Okay? And there were one or two scientists behind this, particularly Leonard and Stark, who actually both joined the Nazi Party. They were Nobel laureates, though. Okay? But they wanted Aryan physics instead of Jewish physics. It's as if physics understands the concept of race. I mean, it sounds ludicrous today, but it happened. It really happened. And it spread around the world. Now, I'm not saying this man was anti-Semitic at all, but he was very arrogant and misguided. He was like Eddington, a former president of the Royal Society, and he taught relativity, at least what he thought was relativity, at Imperial College, but he got it wrong. And it took a while for it to emerge that it was wrong, and eventually decided he didn't like relativity. And he found himself not being able to get published and outside the consensus, and he started talking about cozy clubs, and then cabals, and then conspiracies, and then mafias, and even scientific fascism at the end, okay? Nowadays, you never hear his name. He's disappeared from the literature. The only place you'll find him is on the internet, where people pop up and say, hey, Dingle was right. No, he wasn't. It makes me laugh. Those people probably have one of these, a sat-nav. And sat-navs make a correction for Einstein's relativity. And if you didn't, your position would get wrong by 2 kilometers every day, extra every day, because of special relativity, and 13 kilometers a day because of general relativity. Interestingly, the sat-nav system was first started to be designed the year Dingle published a book, which is a rant against relativity, but he was ignored. They went with the consensus view. They didn't go with the relativity deniers. And that's really important because we have sat-nav as a result. Well, at least we might have had a sat-nav before, but it was one that would have put you in the wrong country after a month or so. Okay? So consensus really matters. It matters for science progress, and it matters for getting science into technology that can help mankind. While I'm having a bit of a rant about the internet, I just want to talk about, has anybody come across MRDA? Okay? It stands for, it's kind of close to my heart, because my father used to work for John Profumo. And MRDA stands for Mandy Rice Davis Applies, okay? That's supposed to spin up like a newspaper in an old movie. I'm not sure it worked, okay? But it comes from the famous quote that she made at the trial of Stephen Ward, he would, wouldn't he? Which is what she actually said, okay? And it's used, for me, it's a whole way of marginalizing a scientist who's saying what you don't want to hear. Okay? He would say that, wouldn't he? Okay? And it's amazing how it spreads. I get emails telling me I'm only going on about carbon dioxide because I'm a Marxist and I want to bring down the capitalist system. I think, really? I'm sorry, if anybody starts talking Marxist doctrine, it bores the pants off me. And actually, that was quite nice because the letter then went on to threaten me and my family. And I thought, well, okay, if you think I'm a Marxist, you don't know who I really am, and so I'm not going to take it seriously. Or I'm told that I'm only doing it for the money, which is really interesting because I've never had a research grant, a penny of research money, to do any work on climate change. I've never asked for one. Okay? So I might say why I do it. Okay? Two things that Mandy Rice Davis and people who use MRDA don't know about scientists. Okay? One, what every scientist longs for, what we live for, what we want is to be famous for being right. What every scientist dreads is being notorious for being wrong. Okay? And the only way that you have a chance of avoiding two and actually maybe even get a shot at one is demands that you're brutally honest with yourself. And actually, if I'm not, I get a little voice in my ear, and it's a voice with an American accent, a very distinctive American accent, and it's this man. because I was lucky enough as a young scientist to attend a lecture course by Feynman, Nobel Prize-winning physicist in quantum mechanics. And he was the most astonishing man. And talking to young scientists, one of the things he says, the first principle is you must not fool yourself, because yourself is the easiest person to fool. And that is so wise, so true, so wise. And another one, reality must take precedence over public relations, for nature cannot be fooled. Public relations, he said that in the 60s. We call it spin now. Okay? You can't spin a scientific fact. A scientific fact is a scientific fact. End of. Okay, so is there a consensus behind climate change? Yes, there is. And I thought, how can I demonstrate that? There's a number of studies that reviewed the literature and things. But actually, I thought the IPCC, people have the wrong idea about the IPCC. Yes, it's run by the UN. The number of people who are employed and paid to work on the IPCC, I can count on 2 hands, all right? There's about 10 of them at most. It's all done voluntarily by the climate scientists themselves, very large numbers, all done according to the principles of peer review laid down by Sir Francis Bacon. Except actually a bit more open than that. You can nominate yourself to be a referee, okay? Put in a bad review and they won't use it. Break the rules of peer review, particularly confidentiality, and you get blackballed, okay? But you would from any journal, all right? Another misconception, it's a review journal. That's all it is, and they organise conferences. It's also inclusive. You'll find Henrik's work in there. You'll find my work in there, okay, about solar control of European winters. It's alongside other papers that go, I'm not sure Lockwood's got that right, but that's fine. There isn't a consensus on that yet. Okay, so the IPCC is the climate community trying to tell you there is a consensus view about climate change. Okay, so yes, there is. Right, I don't have time to go through this properly, but the point I'm wanting to make here is how old this science is. By 1900s, Svante Arrhenius had worked out accurately what doubling carbon dioxide in the atmosphere would do. Okay? It's not in terms of all the feedbacks, but the radiative effect. And it all actually comes down to this equation, which actually is not new by any means. It's Joseph Stephan put it together from John Tyndall's observations 15 years earlier. Boltzmann came along with a thermodynamic explanation. And then critically, Planck, in the work that actually, in fact, it's interesting, what Planck was trying to do was make light bulbs that emitted more light and less heat. So but it was the founding of quantum mechanics and ended up with us all having mobile phones. Okay. I'm not going to go into it. We can work out how much power per unit area we receive from the sun. We've got the total solar radiance, and it doesn't vary much. In the observations, we find it only varies by about 0.1%. And there's a very, very good scientific reason for that, and that is that the surface of the sun that emits is in good thermal contact with the whole of the convection zone, where you've got large-scale motions bringing heat up to the surface. And that has a huge thermal time constant. Okay? So you can't change the surface temperature quickly, so you can't change the emission quickly. To put it in context, if we turned off the power, the energy flux reaching the bottom of the convection zone now, in 100 years' time, we still wouldn't have noticed any difference in the total solar radiance, all right? So it is very, very hard to change the amount of power we get from the sun simply because of the large mass of the convection zone. And that's why it doesn't vary much. Okay, I don't have time to go into this. We can actually look at what would happen if Earth received that power and just re-radiated it according to the Stephan-Boltzmann law. And you can work out the effective temperature of Earth would be minus 21. Calculation first done by Fourier 200 years ago. And he said something must be warming the Earth beyond that. Okay, absolutely right. 200 years ago. Okay, it was predicted. Incidentally, nobody lives at those temperatures. That's the coldest place on Earth. Average temperature minus 16, and there are 5,000 hardy souls that manage to live there all year round. Okay, so is there a greenhouse effect? Yes, and it's a darn good job there is. Okay. Does carbon dioxide contribute to it? I've given the answer away. Okay, this is 24 hours looking back at Earth by a satellite on its way to Mars. And it measured the spectrum of infrared being emitted by the Earth. It's this black line, and the red line is a model fit. Okay? And the key thing you notice straight away are these bite-outs, where there's less, not no, but less power being emitted. And we can identify what's causing them because the molecules in the atmosphere have vibrations at certain wavelengths, certain frequencies, and they absorb. So you can there's a fingerprint of a given atmospheric constituent, and you can see this is one of the carbon dioxide lines. So yes, it is blocking heat from coming out. Has carbon dioxide risen? I'm not going to spend any time on this. There's no observations that show that to argue that it hasn't. And this is actually the level that we find if we analyse bubbles of air that have been trapped in ice sheets. And we're well on the way to being halfway to Svante Arrhenius' doubling of carbon dioxide. We're just about there. So yes, it's risen. Is that rise man-made? There's a number of ways I could show this. I'm just going to show you one, which is the second Seuss effect. And that relies on the fact that carbon dioxide in the atmosphere is exchanged, it's stored in the oceans, but then they give it back, and it's stored in trees, and they die, and they give it back. But some of the biomass gets subducted and gives us our fossil fuels. Now, there's a strange thing that I don't understand, but people who study this stuff do, and that is that biomass, for some reason, likes carbon dioxide that's made with carbon-12 just 2% more than it likes it made from carbon-13. And that isotopic ratio is found in all fossil fuels. So when you burn them, you put back a bit extra carbon dioxide with carbon-12 compared to carbon-13. So what we do is we look at the dilution of carbon-13 over time, and that fall-off is exactly consistent with what we would expect if the rise in carbon dioxide was man-made. It's come from either burning biomass directly or from burning fossil fuels. Okay? There's no doubt. So the answer is yes, it's man-made. Now, what does adding more carbon dioxide increase the greenhouse effect? And there's two arguments used here. What's interesting is they're mutually exclusive. The first argument is that actually it doesn't absorb infrared. But actually, since Tyndall's measurements, we've known that's just not true. Okay? So we can ignore that. The second one is actually, it does absorb, but it's so good that adding some more doesn't make any difference. The absorption lines are said to be saturated. Okay? That actually, I'm afraid, demonstrates a total lack of understanding of how the greenhouse effect works. Let me demonstrate. Here's a carbon dioxide molecule. It's a normal, linear, triatomic molecule. Okay, let's forget about these double covalent bonds. They're not important. We'll have a grey area, which is the molecule. Okay? We give it what we call a short wave. This is solar photon. Okay, one solar photon. It's short wave because the temperature of the surface of the sun is so high. It's high frequency. And carbon dioxide cannot respond at all. Okay? But if we give it a longer wave photon, lower frequency, the sort that Earth transmits because of its lower temperatures, it can set the carbon dioxide oscillating. We call this the symmetric stretch. Or we might give it another one that's a slightly different frequency, and it sets this oscillation going, which we call the asymmetric stretch. Or there's a third one, and it sets off what we call the bending mode. I should say this is greatly exaggerated, okay, just so you can see it. It's a small, high-frequency bending oscillation. Okay, so what happens in the atmosphere? Here it is, an excited molecule that's absorbed a long-wave photon, but it's sitting in a gas that's got a temperature. So what's going on is this, all right? And every so often, one of these interactions allows that de-excitation to happen. It gives off a photon of the same wavelength, and it can do it in any direction, okay? So let's take a look at our atmosphere. Here are lots of carbon dioxide molecules in the atmosphere. The short wave comes from the sun. This is the spectrum because of the high temperature of the sun, and it goes into the UV. Most of that gets straight down to the ground where it warms it up, but not as much as the surface of the sun, thank goodness, and we get a spectrum here being re-emitted like that, okay, at longer wavelengths. And that's where carbon dioxide can go into these oscillations. So there are windows where some heat can escape through into space. But what happens where it can't? And the answer is that it's going to meet a carbon dioxide. It's got no chance of escaping. There's too much carbon dioxide, okay? And according to idea B, that it's saturated, that's the end of it. But unfortunately, it isn't the end of it. Because eventually that will de-excite and send out a photon which gets absorbed somewhere else. And that could de-excite, could come down. But overall, there will be some of these photons that get all the way to the top of the atmosphere. And we call this guy being at the top of the atmosphere. It's not really the top of the atmosphere. What it is a height that is high enough that above it there's so little carbon dioxide that this thing's got a chance of de-exciting and emitting into space. That's what it does. Okay? So what happens when we add more carbon dioxide? Okay? Essentially, these photons have to go further before there's little enough carbon dioxide to escape into space. So more CO2 raises this height, which actually makes it colder. So it emits less. Okay? And here's the spectrum of what it emits. Okay? If it's emitting less, we're trapping in more. Okay? So a warmer atmosphere results. There is no way you can saturate a carbon dioxide line. The only way you could saturate it is the temperature of this went to 0, because then it wouldn't emit at all. Okay? So the idea that adding carbon dioxide could not be increasing our temperature is ludicrous. It just defies the theory that was laid down 130 years ago that actually it will do this. Okay? And nobody objected, by the way. What happened for 60 years that nobody bothered to object? And then suddenly it had some unfortunate implications. Oh, and we've got to find something wrong with it. Okay? That's not how science works.